So, question 11. The first three terms of a geometric sequence, of a geometric series, are these. Because it's a series, I can put plus signs instead of commas in between, because series just means that things are being added up. And P and Q are definitely not 0, it says. So, instruction A, use algebra to show that one possible value of Q is 5 and to find the other possible value of Q. Okay, well, returning to my formula page. These are the main formulas that get all the attention, but don't forget that you can always state a fact using these. Okay, and that's what I'm going to do here. I'm going to say the third divided by the second is the same as the second divided by the first. So P over P 2Q plus 2 over P 3Q plus 1 equals P 2Q minus 1 over P 2Q plus 2. So the third divided by the second is equal to the second divided by the... The second divided by the first is equal to the third divided by the second. Okay, so this is now algebra skills. That's not a red dude, that's just a cancellation of a fraction on the left and a cancellation of the fraction on the right. So we get 2Q plus 2 over 3Q plus 1 equals 2Q minus 1 over 2Q plus 2. I'm going to times both sides by 3Q plus 1. You pretend that you're timesing by 3Q plus 1 over 1, so the 3Q plus 1 hits the top and the 1 hits the bottom, thereby leaving it unaffected. And now times both sides by 2Q plus 2. Okay, so I'm going to expand. And collect on the right. Hopefully this will factorize. Yeah, I think that works. The mouth will be negative 10Q, the nose will be Q, so that'll combine to give negative 9Q, so that's good. So 2Q plus 1 equals 0, or Q minus 5 equals 0. So Q equals negative half, or Q equals 5, which is what we're required to show. Now for each part B, for each possible value of Q, calculate the value of the common ratio of the series. Well, the common ratio of the series is this and this. They're both the common ratio, because that's the second divided by the first, that's the third divided by the second. I'll use this version of it because it's got positive numbers. So the common ratio is, for Q equals negative half, 2 times negative half plus 2, so that's 1 over 3 times negative half, that's negative 1.5, plus 1 is negative half, so that's negative 2. For Q equals 5, it's 12 over 16, which is 3/4. So that's part B. Now, fact. Q equals 5, and the sum to infinity of the series is 896. So A over 1 minus R is 896. We already I was going to say, do we know the first term? We don't know the first term, but we do know the R. If Q is 5, the R is 3/4. So A over 1 minus 3/4 equals 896. So A over 1/4 equals 896. So A 4A equals 896. So A equals 224. Yep, 224. Okay, now what does that mean? That means that P is, so the first term is 224, but we also have an expression for it. It's P 3Q plus 1. For this whole business, Q was 5. So P equals 224 over 16. Divided by 16 is easy. You just halve it 4 times. Halve it once, you get 112. Halve it again, get 56. Halve it again, you get 27. And halve it one more time, you get 13.5. So that's the P. That's part C, and the sum to 2 decimal places of the first 12 terms of the series. So that's given by this formula, A R12 minus 1 over R minus 1. We now know that our A is 224, our R is 3/4, to the power of 12 minus 1 over 3/4 minus 1. You pump that carefully through a calculator and you get the answer. Question 12. There's a savings scheme. It pays 5% per annum compound interest. A deposit of £100 is invested in this scheme at the start of each year. Okay, so I'm going to set up a chart, for a little diagram for this. This is year 1, year 2, this is year 3. There's the start and there's the end. The start and the end. The start and the end. So I'm going to record how much money is in the bank. Now it says that £100 is put in at the start. At the end it gets boosted by 1.05. I'm just going to leave the units out from now on. Then on the first day of the second year, 100 gets added in. And then at the end of that year, this 100 gets boosted by the 1.05, and this 105, that's 105, gets boosted by 1.05 again. Then another 100 comes in on the first day of the third year. And then at the end of the year, this initial 100 gets boosted a third time. This secondary 100 gets boosted another time, and this most recent 100 gets boosted another time. This is an example of just how careful you have to be with questions about money in the bank, because there's a difference between the start of a year and the end of the year. The boost does not happen in many of these questions until the very end of the first year. To show that at the start of the third year, by the way, this was literally just writing out the first terms of the sequence to get in the groove. You should always do that, no matter how much time it takes. Now, part A, the actual job. Show that at the start of the third year, the annual deposit has been made. So just after the annual deposit has been made, the amount in the scheme is 315. So you just add that up, and you will get 315, and that's done. Okay. Part B, find the amount in the scheme at the start of the 40th year, after the annual deposit has been made. So, looking at the pattern here, at the start of the third year, we've got hundreds everywhere. However many terms, whatever this number was is how many terms you've got. The highest power on the 1.05 is one less than the than the number here. So therefore, if that was a 40, I'd have 100 times 1.05 to the power of 39 plus 100 times 1.05 to the power of 38 plus, and no matter what it was at the start of the year, the final term is 100. Now we just decided that whatever this number was is how many terms there were. So if that's a 40, there's definitely 40 terms here. I'm just to add that up in an efficient fashion. Now that is a geometric sequence. I'm going to actually read it in reverse. I'm going to regard that as the first term. The thing you're timesing by each time is 1.05 clearly, so that's the ratio. So this divided by this is the same as this divided by this, which is 1.05, and the n is 40. So all we have to do is put this through a calculator. And that will be the amount at the start of the 40th year. If it asked about the end of the 40th year, that's a different kettle of fish. It'll probably be the same number of terms, but now instead of this being one less than that number, this will be the same as that number. So the answer will be different. This question demonstrates the extreme care required for these questions about money, and the fact that you have to differentiate between the start of the year and the end of the year. In most financial situations, you do not get your money boosted until it's been there for a whole year, and your working should take account of that. Okay, question 13. A competitor is running a 25-kilometer race. For the first 15 kilometers, she runs at 12 kilometers per hour. After 15, she takes 20% longer to complete each kilometer. So that's distance, speed, time. So here's another kilometer. The time, so we'll just do that classic GCSE thing. Speed equals distance over time. So distance is 15. So time is distance divided by speed, so that's 1.25 hours. For the next kilometer, so this is my little calculation for the first 15 kilometers. So 15 kilometers will be done at 12 kilometers per hour. So therefore the time taken will be the distance divided by the speed, so it'll be 1/12. But then for the 16th kilometer, it would be 1/12 times 1.2, because that's what increases it by 12. That's what increases it by 20%. Now what's going on here is that I was very cautious about increasing anything by 20%, so I wanted to do it literally. I wasn't sure whether I should increase the speed by 20% or decrease it by 20%. So I did a calculation, got my time, so that the very thing that I had to increase by 20% was right there. So now I'm ready to start making a sequence. So let's make it I mean, you can make up whatever sequence you like. I'm just going to make it up in terms of time taken for the time taken to do a kilometer in hours, starting with the 15th. So the time taken to do the 15th kilometre is 1 over 12. Then it's 1 over 12 times 1.2. And then it's 1 over 12 times 1.2 squared. So timesing by 1.2. And then it's 1.2 cubed over 12, etc., etc., etc. Okay, so these are times taken to run 1 kilometre. Okay, and clearly this is the first term, this is the second term, this is the third term. So the third term has the 17th kilometre in it, the fourth term has the 18th kilometre in it. So if I want to know which actual kilometre is being running, kilometre it is that's being run, I should take the position, like the term it is, and add 14. Okay, so let's actually start doing the question now. Find the time taken in hours and minutes the competitor takes to complete the first 16 kilometres of the race. So the first 15 we already decided up there was 1.25 hours, which is 1 hour and 15 minutes. And then the 16th kilometre, we decided that that was going to take 1.2 over 12 hours, which is 12 over 120 hours, which is 1 over 10 hours. 1 over 10 hours is 6 minutes, so the answer is 1 hour and 21 minutes. So that's part A. Part B is to show that, okay, so first they introduce a name. They say time taken, so this is part B, time taken to complete the rth kilometre is UR. So R is their name for these things here. Okay, so the time taken to complete the 15th is 1 over 12. The time taken to complete the 16th is 1.2 over 12. The time taken to complete the 17th is 1.2 squared over 12, etc., etc. And our job is to show that UR equals, so we want to show that UR is equal to 1 over 12, 1.2, R minus 15. Okay? Now, that is a formula. Okay? To get a formula into the picture, I can either just do it from first principles, use my brain, or I can use some machinery such as this. The machinery that's most appropriate is this, not only because it looks like what we have to show, but also because these are geometric, is a geometric progression.